This paper attempts to recreate a 3D point cloud structure using only videos as input. We won't go into the details of the paper here, but it looks like it is a well-maintained repository, so we're going to try this out today and see how well it works. We'll be using the CUDA version of the library that can be downloaded from the repository. We've also found a video of a home tour with some nice clean transitions. We'll take about the first 60 seconds of this video and see what kind of results we can get. We'll also downsample the video to ensure that we're not working with too many frames. The COLMAP documentation suggests a particular directory structure. The structure is provided in the Quick Start section of the tutorial. They suggest creating a Workspace directory and then storing your input images in a subdirectory called Images. We'll first create the project Workspace directory, and then we can set up everything else in the script. Let's open up a new Jupyter notebook and get started here. The first thing we'll do is import the path library. The images path is going to be project/images. We'll then use make directory to ensure that the directory exists. The next thing we'll do is download that YouTube video. We'll use PyTube to download the video. And then we'll also need the video's URL. Next, we'll create the YouTube object, which takes the URL as an input. So let's take a look at what streams are offered by this object. And then let's print it out in a nicer format. We're looking for a low frame rate, but we want a high resolution. We want to choose the MP4 version. So let's use the I tag as a way to get access to this particular stream. The streams object in the YouTube library has a function that will allow us to look up this stream based on its I tag. This function is called getByITag. After we get the stream, then we can just call download. So this should download the video. Yep, we see it there. Now we're going to downsample the video. We'll use the OpenCV library to do this. We can create a capture device by using capture video and then passing it the name of the video. Now it's not going to work right away because we still have the video downloading. So now we're going to capture the frames from the video. Alright, it looks like the download is done. And now autocomplete will work here to get us the title. We want to capture an image from the video roughly about every 10 frames. Let's keep track of the frame number in a variable, and then we can get every 10th frame using the mod operator. We will save the images into the image path directory that we set up earlier. So the target is going to be the image path along with the individual frame number, and then we'll also add the JPEG extension. This will be a path object still, and we need target to be a string, so let's wrap this in the string function. And the nice thing about CV2 is at this point we can actually just use the image write function. We'll pass it the target and the frame. As we mentioned earlier, we only want to process the first 60 seconds of the video. We can use the frame number variable to break out of the while loop after we've reached 60 seconds worth of frames. And then we want to release the capture device and we'll print done. One thing we definitely want to make sure we do is during the matching section, we want to avoid this time complexity here. So we want to provide this as a video to COLMAP, which is something that COLMAP does support natively. So to ensure that sequential matching works, we just need to make sure that our images are ordered, which is actually fine because we're already using the frame number when we save the files. So this should work as it is. Oh, in OpenCV, this is video capture, not capture video. Alright, and this shouldn't take very long. We're only taking in the first 60 seconds of images. So let's double check and make sure that we're actually getting some data into our project. Yep, we're definitely getting images into the project directory. We definitely don't want this fade in the beginning. And we want to go until we have 180 images, so it looks like it's almost done. So the next thing we want to do is extract the COLMAP directory. And it looks like we'll have to use 7-zip to actually get it extracted. And according to the documentation for COLMAP, we should be able to just use the GUI. We'll use the automatic reconstruction feature. We'll have to set the workspace to be our project directory, and then the images directory will be pointed to the images subdirectory that we put into our project directory. We don't need to set up a mask folder or a vocabulary tree, but we definitely do need to set the data type to video frames. We will actually check shared intrinsics. This is referring to the camera intrinsics, and since the entire video is using the same camera, it should be fine. We'll do a sparse model for now and avoid the dense model at first, and these by convention should maximize the utilization of the GPU. So let's go ahead and run this for the first time. So it's probably going to run some kind of feature descriptor first, and then it will do the matching. During the correspondence search phase, they're using SIFT for the feature extraction. The matching should be relatively easy. We're using sequential matching, so our time complexity should be better than what's listed here in the paper. The geometric verification section is actually quite interesting. Once they determine the key points in each image, they then use this information to model the camera extrinsics. The next steps are image registration, triangulation, and bundle adjustment. The bundle adjustment is there to recover from drift during sim. We're now in the matching phase. We'll speed through this part. It'll probably take about 10 minutes. Now it's complete. Let's have a look at it. And the first thing we can see here is that it's displaying the camera extrinsics that it had calculated earlier. They're displayed in red. And it looks like it's done a pretty good job recognizing a number of the features in our scene. It seems to have had some trouble with the fine structure of the stairs, but it's done a good job with this reception area on the left. Let's reduce the size of the camera extrinsics so we can see the scene a little better. These chairs here have particularly high definition. Alright, we'll wrap up this video here, but in the future we might try a similar method that can produce higher resolutions. And in particular, we'll want to generate a mesh map rather than just point clouds.